Hey guys, welcome back to chapter 3. In this video, we're going to talk about one of the very important atomic or periodic trends, and that is atomic radius. So the size of these atoms. So first, let's talk about how we measure atomic radius or how we measure atomic size. When we talk about the size of an atom, what we're talking about is the distance from the nucleus to that outermost electron. So we're talking about what is the distance from that nucleus to the outermost electron, those valence electrons. That's how we're talking about atomic size. So here we see, again, that periodic table of just the main group elements. So we've got column 1, column 2, and then we kind of take out those transition metals, those exceptions to the rule, and then smash together 13, 14, 15, 16, 17, 18. Okay, so these are the main group elements. What we'll see here is two trends. We'll see a trend from left to right. We'll also see a trend from top to bottom. Let's talk about the trend from top to bottom first, because that one's a little bit easier to talk about. So, looking at that trend from top to bottom, first we see that the atomic size is going up. So as we move down the periodic table, our atoms are getting bigger. So this one's a pretty easy one to understand. If we look at, let's say, this first group here, we know all of these guys have one valence electron. As we move down the periodic table, the position of that one valence electron gets further and further away from the nucleus. So here that valence electron is in the first energy level. Here it's in the second, third, fourth, fifth, sixth, and so on. So as we move down the periodic table, remember we're stacking these orbitals one on top of the other. So of course an electron in the sixth energy level is going to be much further away from the nucleus than an electron in that first energy level. The trend from left to right is not as intuitive and takes a little bit more work to understand. So going from left to right, we actually see that the atomic size gets smaller. But we can explain this with the knowledge that we have. So let's look at this second energy level here. Okay. So the first thing to point out is the valence electron for all of these atoms is in the second energy level. So they're all in the same energy level. So what's happening as we go left to right? So what we see is the nucleus is going to pull, P-U-L-L, or attract those valence electrons a little bit harder and harder as we move across the periodic table. So here with lithium, in that nucleus, we've got 3 protons, and those 3 protons are going to reach out and try to pull those valence electrons a little bit closer to them. As we move across the periodic table, we get over here to nitrogen. Nitrogen has 10 protons in the nucleus. So now those 10 protons are reaching out to that second energy level and trying to bring those electrons closer to it, right? Positives attracted to negative. So as those 10 protons are reaching out to attract those electrons, it's going to do so with a lot greater force. So it's going to be able to pull those electrons a little bit closer to it. The analogy that I like to use here is lithium has a magnet that's 3 inches maybe in the nucleus, and it's going to reach out and try to pull those electrons close to it. Neon would have a magnet that is 10 inches. So that 10-inch magnet is going to be much more efficient at reaching out to those electrons and pulling them in tighter, pulling them closer to that nucleus. So that's what's happening as we go from left to right on the periodic table. Is those electrons are getting pulled closer and closer and closer and closer to the nucleus. And then we add an energy level they get pulled closer, 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 add an energy level, closer, 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 closer. The official calculation for this is something called effective nuclear charge. Effective nuclear charge is not something that I'm going to ask you guys to calculate on its own. But for my students that are very math oriented, this effective nuclear charge could prove to be helpful in trying to understand this trend. So essentially what effective nuclear charge does is it takes the number of protons, which is this Z value here, so that's the number of protons, and it subtracts it from the core electrons. So remember, core electrons are anything that are not valence. So we see the protons minus the core electrons, and we get that effective nuclear charge. And what we see is as we move across the periodic table, that effective nuclear charge changes, and we see that as it increases, the inward pull of that nucleus is stronger and stronger and stronger. So here's just a nice little summary slide to summarize the things that we've talked about. So the atomic radius increases as we go down the column, and here's a couple bullet points explaining why. And then the atomic radius decreases as we go across the row from left to right, and then here's our explanation as to why that is. So how am I going to ask a question like this? What is it going to look like? So here would be a great example of what a question might look like. So arrange the following atoms in order of decreasing size. So pause the video, give this one a shot, and then we'll solve it together. All right, so to solve this problem, what I like to do is kind of draw a mock periodic table with the trends. So here's my periodic table. Oh my goodness. Let me make that a little bit neater. Here's my periodic table. There we go. And then as we go from the top to the bottom, I know the size is going to increase. And then as we go left to right, I know it's going to decrease. And then I'm going to put these atoms kind of in their respective places in the periodic table, just kind of a rough sketch here. So bromine is over here on the left, about a little bit down. Rubidium is over on the right, and it looks a little bit lower than that bromine. Fluorine is back to the right. It is above bromine. And then potassium is back to the left, and it is right above rubidium in the same line as bromine. So now to rank these, I'm just going to compare them to the atoms that they're near. I'm not going to try to compare all four of them at once. I'm going to break this down and make it a little bit easier, smaller chunks. So looking at potassium and rubidium, they're in the same column. So all we have to consider is going from the top to the bottom. So I know rubidium is going to be bigger than potassium. I can do the same thing here for fluorine and bromine, so they're stacked right on top of each other, so I know bromine's going to be bigger than fluorine. The only connection that I don't have yet is between potassium and bromine. So I know as I move from left to right across the periodic table, things get smaller. So I know that potassium's going to be bigger than bromine based on that. So now we want to arrange these in decreasing size, so the biggest to the smallest. I'm just going to start somewhere, okay? It doesn't matter where. So if I start over here with fluorine and bromine, I know that fluorine is smaller, so it's going to be on the right. My arrows are going to point this way. And then we have bromine. Next, I could do bromine and potassium. So bromine is smaller than potassium. Potassium's a little bit bigger. And then I know rubidium's bigger than potassium. So this would be the correct answer for arranging these according to atomic size. So we put them into the periodic table, compare just 2 atoms at a time, and then try to put them in order for whatever it's asking, decreasing or increasing. I could ask either way. So that is our first periodic trend that is predicting atomic size. In the next couple of videos, we'll look at a couple other trends. I hope you guys found this helpful.